好，那就开始。好，那我就简单介绍一下我英文。Shin Sun is now a research assistant at Dr. Yuan-Chung Cheng's group in chemistry department, National Taiwan University, and his research interest lies in applying advanced computer technologies to chemistry, and he is especially enthusiastic about the potential of near-term quantum computers applications. So let's welcome him. So you can start.
Okay, so thanks for the introduction and good morning. It is a great honor and pleasure to be here to share my research. The topic of my today's talk is engineering quantum noises on IBMQ devices for the dissipative dynamical simulation of molecular systems. And we believe it is a very interesting new application on current quantum computers. And we wrote a paper about this topic. So if you want to know more information about our work, please find our paper at arXiv. And if you have any questions during the talk, please don't hesitate to stop me at any moment. I will be more than happy to answer you. So let's get it started. Okay, so this is outline for my today's talk. The story begins with the idea of quantum simulation. It is not a very new idea per se, but it has since become one of the most popular research topics of quantum information science. After briefly introducing the idea of quantum simulation, we will move on to the limitation of current quantum devices. And in this section, I will explain that although we have a real quantum computer nowadays, but to use it in order to perform useful computations is still a tricky problem. And this is actually the motivation of our research. And in the third section, we will come to the central idea of our project, which is using IBMQ quantum computers to perform dissipative dynamical simulation of exciton systems. And we believe it is a novel and promising application of near-term quantum computers. And finally, I will make a conclusion of what we have done and what we can do better. Okay, so let us begin with the part 1, introducing the quantum simulation. So, although I know everyone here is an expert of quantum information science, but consider the background of the audience might be very diverse. So I still want to start from some easy stories, just to make sure we're on the same page. So in a short word, I would like to call quantum simulation a quantum imitation game. So the idea of quantum simulation is originally proposed by Richard Feynman at 1982. And the essence of it is to utilize a controllable quantum mechanical systems, the so-called quantum computers, to simulate another quantum system one would like to investigate. And it is believed that many quantum systems cannot be efficiently simulated on conventional computers, can be efficiently simulated on quantum computers. And here is the illustration of the process of quantum simulation. So on the left-hand side, this is a real-world quantum system, a chemical reaction. If for some reasons this quantum system we want to know is hard to simulate, hard to implement in the laboratory, the theory of quantum simulation tells us that we can encode the problem equivalently on a quantum computer and simulate the time evolution on this easily controllable quantum system. And then the dynamics we want to know just become like a video tab. We can pause, fast forward, or play backward to understand every aspect of this dynamical quantum system. And this gives us tremendous amount of information about the important system we want to understand. And here's some terminology. In order to perform quantum simulation, we will need many qubits, depending on the dimension of the system we want to simulate. And based on the Hamiltonian of the target system, we can design quantum circuits as propagators, this exponential IHT here, to simulate the time evolution. And I will give some examples to explain this in more detail. Okay, so after a brief introduction about quantum simulation, let us face the truth and understand the limitation of current quantum devices. So actually, to control a large-scale quantum system and maintain its coherence at the same time is a formidable engineering challenge. And current quantum computers suffer from various errors, which can be broadly categorized into two types. The first is of coherent type, and they result from the mischaracterization of the system Hamiltonian. The second is a more devastating decoherent errors. They result from the unwanted system-based interactions. And those interactions will make your quantum computers lose its coherence very fast. So in the following, I will present a very simple experiment we have performed to demonstrate the quantum errors on current quantum computers. But before doing that, I will review some basics of qubits and set the stage. So from basic quantum mechanics, a general state of a two-level system can be represented by the so-called density operator acting on the complex Hilbert space. And due to the hermicity of the density operator, we can decompose it with respect to Pauli basis, and the Pauli operators are defined here. The trace operation is the inner product in operator space, and they correspond to different observables. And once you decompose the density operator, the resulting coefficients can be viewed as components of a vector called the block vector. And by plotting the block vectors gives us a very vivid representation of a qubit state. So by the normalization condition, the trace of the square of the density operator is less than or equal to 1. If the trace square is equal to 1, corresponding to vector with unilabs, this state is said to be pure. And if the trace square is less than 1, the state is said to be mixed, which means that your state cannot be described by a single wave function, but a statistical mixture. And the two most important states are the basis state 0 on the north pole and the 1 on the south pole. Okay, so once we have the block representation, we can very easily see the behaviors of some elementary transformations, which is the quantum gate. So for example, here's the X gate. It takes the state from the north pole to the south pole by rotating around the x-axis. Very simple, right? So it is obvious that applying the X gate twice should be an identity operator, which does nothing. But let us see if this is the case on real devices. So in the following experiment, we initialize the superconducting qubit provided by IBM in full basis state, and we repeatedly apply the X-squared gate up to 300 times. And we perform the state tomography, which is measuring these following observables, and we plot the resulting block vectors. So this is the result. As we can see, this is not an identity at all. So the number here is the length of the vector. So the behavior can be seen as a rotation along the x-axis. This is due to the X gate is miscalibrated on the IBMQ devices. Thus, it is a coherent error. And the second is a uniformly shortening of the block vector. And this is actually a well-known decoherence channel known as the depolarization. So here is our lesson from the X gate. We cannot get the correct single qubit dynamics even for a simple X gate. So we actually live in a very special age of quantum science. On the one hand, many proposals to control quantum systems on various architectures are proposed every day. And we do have some prototypical quantum computers to demonstrate large-scale entanglement. But on the other hand, the quantum devices available nowadays are still very noisy, and the scale is also not large enough to perform quantum error correction. So John Preskill, search term our age to be the NISO era, sort of like the vacuum tube era for quantum computers. Okay, so the real goal of our project is that how can we make quantum computers nowadays useful? And this leads us to the third part, the dissipative dynamical simulation of exciton systems. Okay, so any questions so far? Okay, so if not, we will continue. So the whole motivation of our research is that simulating a closed quantum system on these NISO devices is prone to error due to both coherent and incoherent noises. But these are the very effects required in simulating open quantum systems. So our idea is that can we utilize the intrinsic noises in a quantum computer to simulate open quantum system dynamics? So to demonstrate our ideas, we have to design some proof of concept experiments. And in our proof of concept experiment, we intend to simulate the simplest model for the excitation energy transfer, that is an exciton diamond. The exciton model is a very useful, effective model to describe various chemical processes. And the model contains various sites, and each site is a two-level system. This makes them very easily mapped to qubits, as we will see. So here is the illustration of the model we want to simulate, the exciton diamond. So these are the complete basis states in the site basis picture. And we can see that two sites can be both in ground state or one of the sites in excited state, or both are excited states, denoted by this cat. And one more thing to note is that in realistic modeling of physical systems, these two states are very different in terms of energy than these two states. So these two states will have a time scale separations. So we can often restrict it, the space of interest, to be a particular number of total excitation. So in this case, we focus on the one excitation manifold. And to encode the exciton state on quantum computers, we actually use a very naive way called occupation number encoding. It is almost trivial. And we use 2 qubits as 2 sites, and we encode the occupation number in qubit computational basis. So if the site is in the excited state, we set the corresponding qubit to be 1, and otherwise the qubit is set to be 0. So this is our initial state. And here comes our Hamiltonian. This Hamiltonian is written in the site basis. And for convenience, we model our dimer system as symmetric. So the site energy has no difference. We set them to 0. And the off-diagonal term, which is called the excitonic coupling between the sites, are set to 100 wave number. And to encode the exciton Hamiltonian, we first write down the original Hamiltonian in the second quantized representation. And we employ a transformation called the Jordan-Wigner type transformation. And I'm being very careful here not to call it the Jordan-Wigner transformation, because the Jordan-Wigner transformation refers to the encoding of fermions. But here our system is bosonic in nature, so there's still difference. So after the Jordan-Wigner transformation, we are able to transform the original Hamiltonian to be Hamiltonians for qubits in Pauli basis. And it is very easy to implement the time evolution operator exponential IHT for the Hamiltonian in local Pauli basis. And here is our design quantum circuit for the time evolution operator for the dimer system. And the parameters here in the circuit is the rotation angle, and it is proportional to the simulation time. The explicit formula is here. The angle is equal to the coupling divided by the Planck constant in the unit we used, and times the time in femtoseconds. And we choose to observe the population dynamics for the simulated system. To do so, we perform projective measurements up to 8,000 shots in qubit computational basis at each simulation time. And we exclude the resulting count if the state collapses to 0, 0 or 1, 1, because we said we only focus on the state in the one excitation manifold. Then we can easily calculate the population on the first site to be the number of counts from states 0, 1 and divided by the counts from 0, 1 plus 1, 0. So we sent our quantum circuit over IBMQ cloud and executed it on the superconducting qubits. And we plot the simulation time against the population we measured. And as we can see, the population dynamics is a typical Rabi oscillation. The energy just transfers back and forth between the sites. And this is a fundamental result predicted by quantum mechanics due to the phase coherence between the two sites. And this validates the correctness for the simulation of vacuum dynamics to be compared with dissipative dynamical simulation in the following. So the next question is that how can we introduce the noises into the system to simulate an open quantum system? And actually, we are not the only group on this topic. Many groups have proposed ways to simulate an open quantum system. Just to name a few, Barrio and his co-workers use ancillary qubits and optical pumping on ion-trapped architecture to simulate an open quantum system. Mostame and his co-workers achieved the required system-based interactions by explicitly engineering the qubit resonator coupler to mimic the environment. And this is done on the superconducting circuit. And recently, Wang and his co-workers used MMR quantum computers to simulate photosynthetic convex dynamics. And the coherence effect here are introduced by deliberately and explicitly adding the noises into the control field. Okay, so previous proposals are all based on more qubits and or with explicit engineering to model the system-based interactions. So this is still demanding for NISQ devices because you still assume your quantum computers is perfect, including the ancillary qubits. And the problem is that why don't we just exploit the errors in the quantum gates during the execution of NISQ devices? So our philosophy is very simple. Our philosophy is that quantum computers has errors, so be it, and can we make some lemonade from this? Okay, so this is a general scheme to introduce decoherence into the simulation. So our strategy is simple. We just apply get sequences, which is equivalent to identity operator. As we know, an identity operator do nothing to the system, but on real quantum computers, it opens the channel to introduce various kinds of errors. So effectively, this procedure adds the noises into the simulated quantum system in the interaction picture. Then the system propagator brought the system back to the Schrödinger picture, and measurement is performed to obtain the statistics. Okay, so we can introduce noises by the above procedure, but we must be able to at least control the amount of noises. And to control the strength of the dissipation, we apply identity gates with the number proportional to the simulation time. And the proportionality constant is we call the damping coefficient. And this is what we use to control the amount of noise. And basically, if our system evolved longer, it also suffers more noises. And the amount of noises is determined by the damping coefficient. So we simulate the dynamics using the simplest x-squared gates we previously mentioned on the different damping coefficients to see if we can obtain the correct dissipative dynamics. And when the damping coefficient is low, we can see it is still an oscillation, but with a decreasing amplitude. And here is a clearer damping. But as the damping coefficient gets larger, we can see a large population revival and multi-frequency behaviors. So therefore, we cannot get a consistent dynamics toward equilibrium as the damping coefficients gets larger. So we need to find what is the problem. The reason is that, as we saw in the error example, a large part of the X error was coherent over-rotation. This is a systematic error and not a random error. So the coherent over-rotations actually cause the highly non-Markovian dynamics in our projective dynamics. This is uncommon in practice in a realistic quantum system. So roughly speaking, we need to randomize the error. That is, we want to eliminate the systematic part of the error. And in order to eliminate the systematic part in the decoherence introducing gates, we perform a spin echo type equivalent gate to the X gate. This will compensate the over-rotation error. So the first compensating gate we design is the XZ² gate. And here is how it works. The circle is a projection of the Bloch sphere on YZ plane. And to dynamically correct the over-rotation error, first an X gate is applied. And the over-rotation is turned into an under-rotation by applying the Phys gate, the Z gate. And the over-rotation of the second applying X gate then cancels this under-rotation. And finally, another Z gate is applied to recover the identity. Okay, so due to the phase error introduced by the Z gate, the systematic part is still not cancelled. So we treat this gate as an over-rotation gate again, and we build a higher order compensating pole sequence. So as we can see, in this time, now the coherent error is much eliminated. So we choose to use this as our identity gate to introduce various decoherence in our dissipative dynamical simulation. So this is a good gate in our sense. So the population dynamics under this gate, this time, is much more consistent, and the population dynamics decays faster with increasing amplitude as we expected. Okay, so all previous gates were based on single qubit gate. And a natural question to be asked is that what if we use a non-local gate to introduce decoherence? So we use the entangling gate, the control knot, to construct this swap gate and apply them twice to recover the identity. And here is the specification of the C0 gate. And by concatenating 3 C0 gates, we can swap the state of 2 qubits, and the swap square is still an identity. And to our surprise, the swap gate produced the most consistent dynamics, and the noise strength is also very good. So we can simulate this quantum dissipative dynamics throughout coherent to incoherent parameter regime This covers all range of the dissipative dynamics. Okay, so quantitatively, we see that's the expected results. But we need more quantitative evidence to validate the simulated dissipative dynamics. So we compared our NISO simulations to the dynamics obtained using the hierarchical equation of motion method. The hierarchical equation of motion is numerically exact but expensive algorithms to simulate open quantum system dynamics on classical computers. This method is based on the system-based model of open quantum systems. So all the details of the system-based interactions are encapsulated in this called spectral density. And the hierarchical equation of motion relies on the so-called Drude-Lorentz form of this spectral density. The important parameters in the system-based interactions are the reorganization energy. It corresponds to the system-based coupling strength, and cutoff frequency. It corresponds to the best realization timescale. And we therefore try to fit our results by adjusting the reorganization energy and fix other parameters. And as we can see in the results, in both coherent underdamped region and incoherent overdamped region, they both can be fit excellent. And here are the corresponding parameters. But what I showed to you previously is that we can use quantum computers to reproduce a physically meaningful open quantum system. But for a quantum computer to be truly useful, we must be able to simulate a system with any given system-based interaction strength without actually performing the hierarchical equation of motion calculation. Otherwise, we just know the answer in advance. So in order to demonstrate the predictability of our scheme, we assume a linear relation between the reorganization energy, that is the system-based coupling strength, and the damping coefficient we control on quantum computers. And we use the hierarchical equation of motion to obtain the dynamics at the intermediate coupling region. And we compare it, this is not a fitting. We compare it to the simulation with corresponding damping coefficient at the middle of these two extremes. So the hierarchical equation of motion result is the green line here. And the blue dots are the results for the quantum simulator, for the quantum computer. We can still find an excellent agreement. So this is very, very important. Because in the theory of open quantum system dynamics, the most difficult system to be simulated is when the system-based coupling is intermediate. In weak and strong coupling, we have very good classical algorithms to use, but the intermediate case is much more difficult. But on quantum computers, we can get it right. So finally, since the noises on quantum computers might still be very unstable, so we therefore try to find the relation between noise strength and the damping coefficients on different days. So we perform a series of experiments on different days and fit them to obtain the reorganization energies. And we still assume a linear relation of them. But we can see the slopes are quite different. This means that the amount of noises introduced by IBM's swap gate are not the same on different days, even on the same device. So our proposal is that we could try to run a number of calibration experiments before our actual experiment. And if the calibration curve is built, then we can use the quantum computers to simulate any given system-based interaction strength without using the expensive hierarchical equation of motion. We can just simulate the open quantum system dynamics at any coupling strength just by tuning the damping coefficient here. So we can finally answer the original question. we asked that can we use the noises on quantum computers to do something useful? And the answer is yes. The scheme we propose might turn the not so useful quantum computers nowadays to be extremely useful and natural platform to simulate open quantum systems. And we use a proof of concept experiment to justify our idea. So to conclude, we have successfully simulated dissipative dynamics for the symmetric dimer system on the different damping regime using only the intrinsic gate noises without any additional equipment. And the current IBMQ platform does not offer enough stability for consistent simulation of dissipative dynamics. But by using our designed hardware-specific gate sequences, the consistency can be improved. And finally, we successfully predict the dynamics at the intermediate dynamical coupling regime using quantum computers with accuracy comparable to the state-of-the-art classical algorithm. So here are some open questions we would like to pursue further. First, the detailed characterization of the effect of swap gates for our simulation, or the final control over the best parameters using different gates, or implementing the finite temperature effect for biased dimer systems. And finally, we want to extend our model to large systems with multiple sites. So in summary, we hope the imperfect quantum computers nowadays can help us investigate the open quantum systems beyond what classical computers can do for us. So that's it. Thank you very much for your attention.
Okay. Thank you for your nice talk. Maybe I ask one question and can you go back to the slide of intermediate region? There's a green.
Yes.
Yeah. Maybe I missed something important. So you mean that the green lines is from the HEOM simulations?
Yeah.
And I'm not sure. You mean in the intermediate region is classically hard to simulate, or what I want to ask is how can you get this green line from your classical calculation? Yeah.
Okay, so I mean, to run a hierarchical equation of motion in the intermediate coupling region, you have to make the calculation order very high. There is a parameter in the HEOM called the truncation order. Mm-hmm. And for the intermediate coupling region, you have to set that very high. And that makes your computation very costly. Okay, so this green line is, we say, it is hard for classical computing.
Mm-hmm.
Okay.
So this green line is calculated for a long time, or I missed something, or is?
Yeah, it takes a long time to calculate this green line.
Compared to the
red line.
D equals to 2 and D equals to 80. Okay.
In strong coupling and weak coupling region, we do not have so much order to consider so much order.
So maybe I guess your future direction is calculating some task that is uncalculatable by the classical computer, but you can get it from common.
I want to simulate a system that's barely computable on classical computer.
Even without this green line, you cannot. Yeah, I think.
Yeah, so I have to do some sort of extrapolation.
Okay.
Just like the quantum supremacy experiment.
Okay. Yeah, that makes sense. Yeah.
That's the interesting part.
Any questions?
Yeah, any question or comment as well?
Maybe I ask, can you explain the HEOM simulation again? Why is it expensive? And then, because it looks to me, it's simulating this kind of Lorentzian-like model, so why it is hard to simulate?
Okay, so to explain, the hierarchical equation of motion actually relies on this spectral density, and to actually calculate the propagator or the propagation of the system, we need to recursively solve an equation of motion. And that equation of motion contains many auxiliary density matrices. And if the system-best coupling is very strong, you have to truncate the auxiliary density matrices to a very high order. So in an actual computation, you will need a lot of memory and time to finish that.
So you mean this is a classical simulation?
Yeah, you are solving a very large recursive relation of matrices by performing this hierarchical equation of motion. That is a very intricate classical algorithm.
And compared to the quantum simulation, how do you control the base parameter? Because
yeah. And in the quantum computers, we just control the so-called excuse me, the damping coefficient. And the damping coefficient is the number of identity gates here divided by the simulation time. So the damping coefficient is, if the damping coefficient is big, that means in the unit time, you apply a lot of identity gates to the quantum systems. So we use the number of identity gates to control the amount of noise. I believe that is corresponds to the reorganization energy in the hierarchical equation of motion method. So these two are somewhat physically equivalent.
So you use the number of identity operator to control the strengths?
Yeah, exactly.
So what's the assumption you made? You assume all the identity have only dissipative error and no others, or what's the assumption there?
Yeah, we just assume that the amount of noises in an abstract way, it is proportional to the number. So that is why we assume a linear relation between the reorganization energy and the damping coefficient. This is our first model, and we will want to build more sophisticated model further. But as we can see, this model is actually pretty good.
Okay, I see. Thank you.
Thank you.
So, any other questions? Maybe I ask one more questions.
Yeah.
Can you go back to the case you mentioned is fail to reproduce some interesting results? Yeah. So it means that if you increase your dissipative numbers to 15 and to 70, you get a result that is not the correct answers, or what? Maybe I didn't get the key point. Yeah.
Okay, so I think that the key point here is that this large of population revival or multi-frequency behavior is uncommon or is very pathological in a real quantum system. In real quantum system, in a real world quantum system, as the damping coefficient gets higher, as the system-best coupling strength gets higher, you just see the population damps faster, and it will become this incoherent transfer. It will not be like this. This is a very pathological case.
Okay.
Yeah.
So do you have reasons that why you will get these two unexpected results, or is what I want to ask? Yeah.
Okay, so my interpretation for this is that it is because of the over-rotation error in the x-squared gate.
Okay.
So the over-rotation error in the base actually corresponds to a very large non-Markovian behavior of the dynamics in our systems. So you will see sort of like this.
Oh, okay.
So
thank you.
in a normal, in a realistic BAS, your BAS will not have a systematic evolution. Your BAS is what we call the thermal equilibrium. It just contains the random fluctuations. It does not involve systematic.
Okay, thank you, sir.
Thank you very much.
Sorry, can you explain again the parameter D?
Okay, of course. Let me get my paper. I have a definition here. Damping coefficient is defined as this. The T is the total simulation time, and the delta TD is the unit simulation time, and the Ni here is the number of the decoherence introducing gates. That is the identity gate.
So once you set up your simulation, the parameter is already there. It's not a calculated. I mean, it's not from the simulation result. It's from the setting.
Yeah, it is what we control before the simulation.
I see. Okay. Thank you.
Any questions? Yeah.
So, I have one question. So you say that your method can be applied on exciton model. So did you expect that your method can extend to other kind of physical system?
Yeah, we think it is possible because actually other models can be effectively transformed to the exciton model. And the dimension will be very high, so it might not be affordable on current quantum computers.
Okay.
Yeah.
So other questions?
The exciton model is because it is most naturally mapped to qubit, because it is just a qubit, basically.
Okay. Okay.
But other quantum systems can be mapped to two-level systems.
I see. Thanks.
Maybe I ask one more questions. Have you test other gates beyond swap gates? Yeah.
Okay, so because IBM Q, the primitive gate is the C0 and the single qubit rotation, the X gate. The Z gate is the virtual gate. You just add a phase shift. So we just focus on the X gate and the C0 gate because all other gates will be compiled to these gates. Yeah. So we choose to use the primitive gate.
Maybe I think in other systems like ion trap, you can.
Yeah. The native gate is different. For example,
different.
the XX gate or XY gate.
Because you are using your superconducting qubit.
Yeah.
That makes sense. Yeah.
Yeah, and it might give us more interesting noise characteristics. Yeah. But ion trap, I think this might be not so ideal because ion trap has too low noise. Maybe we cannot introduce the noises enough to make the system decoherent.
Okay. Very good.
Yeah, so our proposal is sort of hardware dependent or hardware specific. So we turn the quantum computers into an analog simulator for open quantum systems.
Any other questions or comments? So if not, thanks speaker again.
Yes, thank you very much.
So maybe we